Okay, welcome back. We had some homework over the weekend, some calculations of isotope ratios, and if you still feel a little bit shaky on those, please start or continue a discussion thread for that. And Jenny and I and your other classmates will definitely give you some tips. Here's our study outline for today. I want to make a mention, a week from today is our next midterm, exam 3, and so it will have everything this week. You can bet that there will be an emphasis on isotope ratios and asteroids, comets, and so forth. And also, the stuff that we're studying today and Thursday is also really important, because we're going to be talking about one of the key tools of astronomers around the world, and that's the Hertzsprung-Russell diagram, also known as the HR diagram, also known as the color luminosity plot. And so we're going to be talking about luminosity and so forth today, and some other things. Last time we talked about energy, and we talked about power in the metric system. Let's do a quick review of that. The example that I gave you is kinetic energy, which you may remember from science class in high school or one of your other science classes here. The formula for kinetic energy, which we don't really work with too much with stars, but for terrestrial objects, 1/2 mv squared. And I'm giving you some examples here of terrestrial systems that you can rate their energy of motion, their kinetic energy, in terms of the metric system unit of energy, the Joule. So one example, I said, take a 2 kilogram object and move it at 1 meter per second, and its kinetic energy, 1/2 mv squared, you calculate it out, it's exactly 1 joule. And just so you know, 1 meter per second, that's about 2.24 miles per hour. So you can jot that down if you like. So in other words, that's a normal everyday speed. You yourself can attain a speed from here, between here and Chick-fil-A at 2.24 miles per hour easily, in order to go over and get some chicken fillet nuggets and stuff like that. Matter of fact, you can easily motate at double that, 2 meters per second. That'd be about 4.48 meters or miles per hour. That's a walking speed, or maybe a jogging speed. Bumblebee Camaro, the quarter-mile test from a couple years back, 115 miles per hour on the quarter mile. That corresponds to 2.2 million joules, or 2.2 megajoules. And the megajoule, capital M, is the usual prefix for that. That stands for 10 to the 6 joules, 1 million joules. So jot that down. We're going to do a little scientific notation clicking here in just a second. So get your calculator out. And if you can handle scientific notation on your calculator, it's going to be an advantage to you. And you can't use your cell phone on the test. If you don't have your calculator on the test, you'll have to go pencil and paper, and I will be showing you how to do pencil and paper today. But if you can do this scientific notation stuff with your calculator, more power to you. It's not hard. You just got to get used to some different buttons and just try things out, get the hang of it. Anyways, megajoule, 10 to the 6 joules. Space shuttle, I looked this one up this morning. The normal mass of the space shuttle is on the order of 100 metric tons, 100,000 kilograms. All right, and when it's on orbit, its orbital speed is about 77.43 meters per second. Now that's like 17,000 miles per hour. Just multiply that number by 2.24, and it's about 17,000 miles per hour. It's pretty, so it's up there on orbit, it's really booking. But then, of course, when it gets down to the Kennedy Space Center landing facility, it lands at about, I think it's either 100 or 200 miles per hour. So it bleeds off a lot of kinetic energy as it comes to the atmosphere. Anyways, its kinetic energy on orbit, 2.998 times 10 to the 12 joules. 10 to the 12, that's a terajoule. Okay, capital T is the abbreviation for that. And so roughly 3 terajoules for the space shuttle. And that's 1 times 10 to the 12 joules. So we're going to do some scientific, make sure you get these examples of scientific notation. Because now that we're working with stars, not planets, even more necessity of handling stuff using scientific notation. It's going to become more and more necessary. Now, I want to see if somebody is here that I asked to sit up in front. Okay, I don't know. I guess everybody's here. All right. Now, that may seem like an awful lot of kinetic energy, and for us, on a human scale, yeah, 3 terajoules, that's a lot of energy. And, you know, here's another way to think about it. 3 terajoules is even more, or excuse me, is even smaller than the total energy stored in these solid fuel rocket boosters and in the liquid fuel. That's the big red tank in the middle. And those babies have a lot more than 3 terajoules because they got to get it up there, and they got to get themselves up there to that altitude, or most of the way to that altitude, plus the space shuttle itself. So those tanks, those things are, you know, lots of joules of energy stored in them and then converted into kinetic energy. So that seems like a lot, but compared to the SUN, oh my goodness. Now here's a picture from 9 p.m. last night. This is a false color ultraviolet picture from the SOHO spacecraft. Here's the luminosity. This is what NASA quotes for the luminosity of the sun. 3.828 times 10 to the 26 joules per second that blaze off the surface of the SUN in all wavelengths. Okay, so this is a false color false color ultraviolet, but you know the sun puts out a lot of ultraviolet. It puts out a lot of visible Roygbiv wavelengths. It puts out a lot of infrared as well. Now let's go through some of the specs on this. So this is a false color, and the SOHO spacecraft, which just type up SOHO, S-O-H-O, and observatory. And they consider it an observatory, and you'll get to their website. And you can look at these pictures every day. They take these ultraviolet images every day. Right now, the sun looks pretty quiet, don't you think? It's not too bodacious. Sometimes it's all blazed up with sunspots and stuff, which show up nicely. So this is about 9 o'clock last night at the wavelength. You know, so they had a filter on for 171 angstrom units wavelength. Now, the Greek letter lambda is the customary symbol. We're going to be using it out the wazoo now. That's the customary symbol for wavelength, lambda. Okay, so angstrom units, that's a metric unit. And at the wavelength 171 angstrom units, or 17.10 nanometers. Yeah. Okay, that's another wavelength. What is a nanometer? A nanometer is 10 to the minus 9 meters. a billionth of a meter. So an angstrom unit is 10 to the minus 10 meters. Now, angstrom is named after some Scandinavian guy named Professor von Angstrom, and who did a lot of, I think he did a lot of spectroscopic work, you know, interpreting spectra and stuff like that. Anyway, so it's named after him, but most of the time we use nanometers, but some people still work in angstrom units, so we need to at least kind of know what they're talking about. Now, this is true scientific notation, my wonderful students. Scientific notation is something point something something, you know, or something point something something something. So a whole number and a decimal point, and then maybe a few more whole numbers, okay? So it's got to be, and then times 10 to the minus 12, or 10 to the positive 26, or 10 to whatever power. So you adjust the power so that the number part in front is somewhere between 1 and 10. 1 and 9.99, all right? So 17.10 times 10 to the minus 9 meters, yeah, that's nanometers. And if I were giving you a written test, I would mark that correct. But like on clicking and in web courses, I would have to specify a certain number. All right, so I would tell you, get it down to nanometers, or get it down to, you know, and so I'd have to spell it out for you in this way. All right. So I might ask you how many nanometers. Usually I don't, excuse me, I might ask you how many angstrom units or how many nanometers. And usually I stick to nanometers. But, you know, all these numbers here are kosher. They'd be considered correct on a written test. On a clicking item, you'd have to, you know, get the exact one that I asked for. Now, what does the blue false color signify? Well, that signifies or identifies the part of, and actually this is not the surface of the sun. This is the atmosphere. The sun has a very tenuous, low-pressure atmosphere, but it's really HOT. And this, wherever you see it blue, the brighter blue, the higher the temperature, and this is the more of the stuff at about 1,000,000 Kelvin. So this is really hot. And this is one of the mysteries of the sun. You know, the surface of the sun, as we'll find out here, is about 5,800 Kelvin. And we can get 5,800 Kelvin temperatures here on Earth, no sweat. 1,000,000 is a little harder. But 5,800 is what we define as the surface of the sun. And for some reason, as you go out into the atmosphere of the sun, it gets hotter. You know, like here on Earth, as you go up into the atmosphere, it gets colder. You know, like if you're up there in a jet airplane, like I was a couple weeks ago, you know, if you could roll down the window and put your hand out there, your hand would freeze solid in about a second because it's really cold up there. All right, top of Mount Everest, the same thing, 29,000 feet. That's about the same height as an airliner flies on cruise at altitude. It's really cold up there at the top of Mount Everest. But for some reason, the sun, and we don't, you know, there's guys that are working on why this is true, but, and the SOHO spacecraft is dedicated to trying to figure out the atmosphere of the sun, among other things, and why it's so hot, whereas every other atmosphere we've ever studied, things cool off. And we have some ideas. You know, we think it's related to the magnetic fields and sunspots and stuff, but the exact physics of it we're still trying to work out. So the sun has got a huge amount of joules per second. Now that's not energy. Joules per second is not energy. That's energy per second. That's a power. Okay, so the unit of power in the metric system is the watt, 1 joule per second. All right, and A good example of watts is something from everyday life, a good old light bulb. This is a 60-watt bulb. I don't know if you can still buy them, but I hope everybody in here remembers the day, when you went to the light bulb store, Home Depot or the grocery store or what have you, to buy light bulbs, and they come in 100 watt, 120 watt, 60 watt, 40 watt, 75 watt, all different variations. And I want you to make a note here. A 60-watt bulb is incandescent, just like what we had up here in the front of the lecture hall on the first day of class. We looked at an incandescent light source. It was emitting light because it was hot. And the 60-watt light bulb is also emitting light because it is hot. Unfortunately, that is a very inefficient process. A lot of energy that goes into the light bulb doesn't come out as light. Most of it comes out as heat. And you can use them to heat things up. Light bulbs are, like we used to try to protect our mango tree out in the backyard with light, floodlights and stuff in the winter, when it was getting cold at night. And a lot of people do that and so forth. But, nowadays, I just want to show this to you. This is what you see in the hardware store, the Publix and whatnot. These are LED bulbs. Now, look at it carefully. See, it says 60W, 60 watts. But those aren't 60-watt bulbs. If you look more carefully, you'll see that they publish that number 60 watts to mean that it replaces a 60-watt incandescent bulb. It only needs 8.5 watts to operate. And an LED light is considered very efficient. It's still not 100%, but it's way more efficient than an incandescent bulb. So it only takes 8.5 watts for an LED light bulb to produce 60 watts worth of light from an old-fashioned bulb. And the distinction here is the following. The LED is not an incandescent source. All right, so you can't compare an LED to the sun, but you can compare an incandescent light to the SUN. And so the sun, we've already looked at this rating, 3.828 times 10 to the 26 watts. Another unit that astronomers use is simply to say, all right, if they're looking at some other stars, how many times the luminosity of the sun does it have? So for instance, Sirius has a luminosity of about 25.4 solar luminosities. And that symbol there is capital L for luminosity, and then the subscript is a little circle with a dot in the middle of it. That's the symbol for the SUN. And sometimes you see a capital L with a subscript SUN. Okay? Due to the fact that some typesetting systems don't have that symbol, the circle with the dot in the middle of it. But my Macintosh does, so we're going to try to use that. Anyway, so that's another unit, and it's just a little bit better because, a watt is, terrestrial scale. But the sun, talking about the luminosity of the sun and rating other stars in terms of the luminosity of the sun is actually pretty good to do because the sun is an average star. It's not the brightest star that we've ever observed. It's not the dimmest star that we've ever observed. It's kind of in the middle. So there's stars below it, like 0.2 times the luminosity of the sun. There's stars like Sirius above it, 25.4. And you can look up any star in terms of the luminosity of the sun and see how many multiples of the sun's luminosity there are. All right. Now, we're going to do a little bit of practice with scientific notation. As I've alluded to, here's a website that has all the prefixes, you know, like tera, giga, mega, kilo, and then nano, and you know, milli, and all that stuff. Here's the shortened address for that. Just go ahead and jot this one down if you're actually physically writing notes on paper. And you know, you can find all kinds of other websites with listings of the prefixes and the powers of 10 that you use for scientific notation. You know, scientific notation is basically just working with numbers, but in physics, you know, we sometimes want to mention, you know, a number without having to write down scientific notation. So it's also nice to know the abbreviation tera for 10 to the 12, giga for, you know, 10 to the 9, et cetera, et cetera. All right, and giga is a billion, and your cell phones operate at in the gigahertz frequency range. You know, depending on what, you know, and over in Europe it's slightly different, but gigahertz, that means a billion electromagnetic waves through your system per second. A billion, you know, so if you have a frequency of 2.1 gigahertz, that means 2.1 billion electromagnetic wiggles, 2.1 billion electromagnetic waves are emitted and received by your cell phone every second. You know, and the variation in the amplitude, and actually there's frequency variations as well that carry data, just like there is on the internet. You know, the whole idea of bandwidth is about frequency variations. Anyways, let's do a little mini workout using iClickers now on scientific notation. And so if you're in space and you're part of the planetary defense and you're in the Dragon capsule like this and you need to do a little bit of scientific notation, sometimes you can do it in your coconut. Let's try question number 1. Read this one carefully. And why don't you write it down in your notes so you have a good example of scientific notation. This is lecture 21. All right, 30 seconds, starting now. Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, most of you got that correct. 4.5 times 10 to the minus 5 kilograms. Okay. All right, let's try this one. Question number 2. Okay, how do you handle multiplication? 3 times 10 to the 8th times 2.4 times 10 to the minus 3. And that number, 3 times 10 to the 8, that's the number of meters per second in the speed of light. And the speed of light factors into the fusion reaction that we're going to be studying today. So this is something that has to be dealt with. 30 seconds. Uh-oh. Yeah, we're okay. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, I was looking at that. Yeah, most of you guys got that right. I was looking at that and I thought, oh, wait a minute, I forgot a decimal point, but A is the correct answer on that one. And so let me just point out to you that Appendix C in our free online textbook at OpenStax has got a bunch of extra concepts. So if you want to double check that, if you're still feeling a little shaky, they got a bunch of examples and whatnot in there. I did it again. I have to pause the podcast. All right. So scientific notation, Appendix C, very good. Now, I want to go through another energy production process with you, and this is the nuclear process using the famous equation E equals mc squared. Now, Albert Einstein is the one that developed this for the first time, and nuclear power is derived from this, because what we think happens is that the nucleus of an atom, if you split it or if you fuse it together with another nucleus, you can produce energy. So fission, nuclear fission, means you split an atomic nucleus like uranium, and when you do that, you actually, you break it apart into other pieces, and the mass of all those pieces is slightly less than the original uranium atom and the neutron that broke it apart. So here's a diagram of that. All right. Now this red dot over here on the far right, right over here, right over. See how this is, right. Oh man, my eyes are hurting. Whew. Yeah, that red dot, that's a neutron plowing into a uranium nucleus. So the neutron is red and the protons in the nucleus are light blue in this diagram. And then in the second panel, the middle panel, that nucleus is split into two what we call daughter nuclei. Okay, so the original uranium on the left panel is the parent, and then the daughter nuclei are split, one's going upwards and one's going downwards. And then you also get a couple, three other neutrons flying out. So you can see those flying to the right and aiming at other uranium atoms. And if they're fast enough, at just the right speed, they'll split those babies. And when they split, the middle panel is where you get the energy production. And so you get this chain reaction, So from this one, you get 3 outgoing neutrons. And let's say that all 3 of them split another nucleus of uranium-235. All right, and then those 3 nuclei produce another 3, each of them produce 3 neutrons, and those split another, each of those neutrons splits another uranium-235 nucleus. So now you got 9 fission reactions, and it rapidly multiplies out by powers of 3 or powers of 2, depending on the reaction, depending on the number of neutrons that come out, and you get a chain reaction. It gets bigger and bigger. And then we have to figure out ways to control it if we want to have a nuclear reactor. If we want to have a weapon, we just let it, fission the entire piece of uranium, as much as we can anyways. All right, so that's nuclear fission. And the important thing is that there's missing mass at the end. At the end of the second panel, there's missing mass. There's 2 daughter nuclei and a bunch of neutrons, and the mass in kilograms of those constituent parts that have been broken out of the original nucleus, they are less mass than the initial components. All right, so there's missing mass. All right, now fusion means something slightly different. Right? Now, fusion reaction means you take two light nuclei, like a deuterium and a tritium nucleus in this picture, and you fuse them together. You fuse them together and you get a helium nucleus, 2 protons and 2 neutrons, and you get that neutron out. Now, that outgoing neutron is available to other fusion reactions. Right? So you could fuse it with a hydrogen nucleus and get a deuterium nucleus. Right? And so this is a fusion reaction. And the same thing here, there's a tiny bit of mass that's missing. It's very, very small. But a little bit of mass goes a long, long way. You get a whole lot of joules out of even a single gram of mass converted to pure energy. Right? So let's work that out together. The sun and the stars are powered by fusion. Let's work out how that works. All right, so there's my equation, equals mc squared. Now, c is the speed of light, 3 times 10 to the 8 meters per second. All right, so that's good. Now, this equation, up at the top, the first line of this equation block, is equals mc squared. So, all right, 3 times 10 to the 8, and we got to square it. So the square of c is 9, and then the square of 10 to the 8, that's 10 to the 16. And it's meters squared per second squared, because you got to square that as well. All right, now you multiply that by a gram, a kilogram, a nanogram, any kind of a unit of mass in the metric system, and you get a joule. So let's take a single gram, 1.00 gram. All right, that's 0.001 kilograms. All right, so 0.001 kilograms times c squared. Hey, you guys, that's 9 times 10 to the 14 joules of energy. That is a lot of joules. All right, and that is why you can have, for instance, in a these big nuclear aircraft carriers, gigantic, 100,000 tons of ship, 100,000 tons displacement, and they can take, a few kilograms of uranium, and, it'll last for years to provide energy in their nuclear. And I think the big nuclear reactor, or the big nuclear carriers, have 2 reactors, if I recall. Now, the nuclear submarines, they have just 1 usually, right? And they have a very small slug of uranium in there, but it's enough. And it doesn't all convert into, the constituent particles, a very small fraction in the useful lifetime of a nuclear reactor. So it's unbelievable. That's a huge amount of energy. All right? And that's just 1 gram. My wonderful students, a gram. You may think, Dr. B, who cares about a gram? Yeah, a gram is the same mass roughly as a paper clip. So, the Star Trek, they have these matter antimatter engines, with the dilithium crystals. Matter and antimatter is not science fiction, my friends. Matter, we don't have a matter antimatter reactor. Actually, we do, I should say. Every nuclear reactor that we have it's convert. No, I shouldn't say that. But a matter antimatter converts all of everything into pure energy versus, nuclear fusion converts a little bit of the mass. You still have a lot of regular grams of matter afterwards. Anyways, antimatter is not science fiction. We work with it every day of the week, twice on Sundays. And, it's nice, Scotty, the engines can't take it much longer and all that stuff. It sounds nice back in the 60s, you know, science fiction TV show with Captain Kirk and Spock and all that stuff. But even in the 60s, we knew, no, it's not science. That part of it's not science fiction. You know, we don't have a reactor for that like they do on TV, but we do know all about antimatter. Now, the sun converts about 4.2. Take my phone off. The sun converts about 4.26 times 10 to the 9 kilograms. So that's 4.26 million metric tons per second. All right, so you may think, dude, 4 million metric tons per second. The sun is, no. The sun has got a huge number. You know, the mass of the sun is like 2 times 10 to the 30 kilograms. You can look at all this stuff up on the NASA planetary fact sheet, and they've got an adjunct, you know, for the solar fact sheet as well. There's roughly, you know, what the sun burns up per second is roughly 4 point something parts per 10 to the 20. I don't even know what that is. 10 to the 20. I mean, it's more than 1 part per trillion. It's more than 1 part per quadrillion. Let's see, what would it be? 9 is billion, 12 is trillion, 15 is quadrillion, 18 is sextillion. So this is 100, like 400, 1 part or 4 parts per sextillion of the sun is being greased into energy. So the bottom line for us is the sun can fuse at this rate till the cows come home, my friend, billions of years. And that is why, one of the reasons that we know that the sun is very stable. You know, it's not burning, it's not like a Roman candle, you know, that goes, you light it, and then in 5 seconds it's done. You know, the sun is just going to keep on cooking at this rate. It's perfectly happy. Its total mass is not changing very significantly. You know, eventually it'll have converted a bunch of its mass, but it's not very quick. So on a day-to-day basis, you know what Julius Caesar saw 2,000 years ago, and you know, all the ancient Greeks and all the Egyptians and the, you know, Mount Vesuvius and all that stuff, pretty much the same, you know, as today. And 5,000 years from now, you know, when your great-great-grandcestors or your great-great-great-grandchildren are orbiting Mars for, you know, Disney World Mars, or whatever they have up there in Mars on an excursion, yeah, it's going to be the same. So the sun is cooking. And for us, you know, the sun is this big fusion reactor. Let me close about the sun by saying this. On Earth, we have nuclear reactions that work with fission of uranium and plutonium, all right? They work at a much lower temperature, and they're still pretty tough to work. You got to build a really strong, tough reactor vessel. We know how to control it. You know, we use all kinds of what they call moderators that absorb some of the neutrons, kind of keep the reaction from going out of control and blowing up. You know, a nuclear weapon, you just let it, you don't have any moderators, you just let it blow. Okay, but a reactor, so the reactors that we have here on Earth, we've got them. on ships. We've got them on land for power. They work good. We've got, pretty good, except for the Russians. They tend to screw around with their reactors over there in Russia. This whole Chernobyl accident, before you guys, most of you were born, Chernobyl was some idiot in Russia, in the Soviet Union, deciding, oh, well, let's do a little experiment. Let's do a little science project with this big reactor in Chernobyl. And they didn't know what they were doing, and the thing blew. And it spewed huge amount. The whole countryside there in the Ukraine is poisoned for thousands of years. It's like quarantine. You can't live there. Thousands of square miles, just because, and it polluted. But all over the world, people were picking that stuff up in the atmosphere. So they, but hopefully, and even these jokers over there in North Korea are a little bit more careful than those guys in the Soviet Union back in the 80s. Anyway, so we have a pretty good handle on fission reactors. We are working on fusion reactors. That movie, what was it, Spider-Man 2 or Spider-Man 3 with Doc Ock, the power of the sun, and all that stuff. That's really a thing that people are trying to work on. How do you contain a nuclear fusion reaction with hydrogen as its fuel? The hydrogen from water will work just fine. How do you contain that? Because it's so much more powerful. It creates so much more heat. It operates at millions of Kelvin, and we don't know how to control it. We have some ideas. We're trying to control it, using lasers and stuff. And, members of my family have been involved in that process, inventing different kinds of fusion systems. But we don't have a handle on it. When we do have a handle on fusion reactors, everybody's power bill, I wonder what will happen, because all of a sudden overnight electricity will be like, your power bill will be down. I mean, it might even be free. It'll be so inexpensive, you could probably give it away for free, or $5 a year, or just enough to pay for the wiring. Because there's so much water, and even a gram of water, a gram of hydrogen from water converted into pure energy is a huge amount, right? So once we get a fusion reactor, the country that gets a fusion reactor first is gonna, it'll obsolete almost everything, and probably we'll have electric cars. And those will go down in price. Everything will go down in price. What else will happen? We'll start using a lot more metal like aluminum. The price of steel, the price of aluminum will go down into, to pennies. Yeah. UW-Madison actually has a fusion reactor. There's a lot of fusion reactors, but they don't work. They're not producing. Jenny's over here saying, "Oh, University of Wisconsin and Madison has a fusion reactor." Yeah, there's reactors all over the place, prototypes, but nobody's. Believe me, the day somebody gets one to cook and produce electricity, that's going to be headline news for years to come. The price of everything will change because we'll just have, extremely abundant energy. So the lesson about fusion reactors is they work at such a high temperature, millions of Kelvin. We don't have the technology yet to handle them. But the sun, how the sun handles fusion? Gravity. Good old gravity. The apple falling out of the apple tree. The sun has so much mass, and only the core of the sun is fusing. The outer layers of the sun, they're pressing down on the core. And the size of the sun is controlled by its mass. The size of the sun is the perfect size to have enough mass to contain the fusion reactor in the core. And we got this, the sun's got a spherical fusion reactor. And it doesn't need any technology other than gravity, because all the outer layers of the sun, by good old universal gravitation, contain it, right? And the heat comes out, but it doesn't. The sun doesn't blow up. It's very stable. It's called gravitational equilibrium. It's a self-gravitating system with a fusing core. So the physics of it, the thermodynamics of it, are pretty complex. But the sun is very stable, and it has a self-contained fusion reactor. Now, I want to go to some other topics. The color and temperature of incandescent objects. Now, this is something that applies to light bulbs and to stars. The sun is a complex object. So the sun is not like those tubes of pure helium and hydrogen and neon that we looked at on the first day of class. Those are pure systems getting zapped by high voltage, and so they emit light for that reason. But they're not incandescent sources. If you get something hot, it'll produce light, and the amount of light that it produces, and in fact the color of light that it produces, depends on temperature. Now, everybody in here has likely seen a stove at home in the kitchen, and you turn it on, and it might not be red hot, but you can still feel the heat. And if it's on low, you get your rice cooking, and then you turn it down to low, and the burner's not red anymore. But when you had it on high, it was red hot. All right? So that whole idea of color and temperature, and if you have something really hot, like in a steel mill, where you have these big furnaces, a big steel furnace, that stuff can be white hot. All right? And what that means is it's got a lot of colors other than red. So here's a really important diagram, okay? And you can see, I'm sure there's one like this in our textbook. I don't think this is from our textbook, though. And what this does, go ahead and make a sketch of it. Vertical scale is relative intensity per square meter, all right? So square meter for square meter, the more temperature you have, the more intensity you have, the more light that you produce. And on the bottom is the wavelength of the light. All right, so ultraviolet is to the left, infrared is to the right, and right down there in the middle, see that rainbow area? That's the Roygbiv visible light. Now remember, I believe I mentioned this already, Roygbiv is the famous name of a scientist whose first name, middle initial, and last name correspond to the order of colors from cool to hot. R, red, O, orange, Y, yellow, G, green. So green's kind of intermediate color and intermediate temperature. Blue, indigo, and violet, Roygbiv. And you can see that, and actually this is Vib-G-Yor. This is violet on the left. So this is Roygbiv backwards here in this diagram. But now, this first curve here, okay, this blue one, corresponds to the, square meter for square meter output of a 15,000 Kelvin star. And it could be anything at the temperature of 15,000 Kelvin. And it goes, so it's sorted by wavelength. So you can see here that the peak wavelength right up here for the blue curve, this is known as the spectrum, the peak there is way in the ultraviolet, all right? And we know that, that false color image of the sun, that was where the parts of the sun's atmosphere were 1,000,000 Kelvin, right? So that's a little bit hotter even than this. So a 15,000 Kelvin star it's going to be putting out Roygbiv, and you can see that over here, all right? It's going to be putting out a good amount of Roygbiv. It's going to look blue because the top color here is violet, and the least intense color here is red, all right? So it's going to look more blue than, another star. But even in ultraviolet, it's where it's brightest. So we can't see that by eye, but we have devices to measure ultraviolet, no problem. All right. Now the sun is about 5,800 Kelvin. All right, and you can see that the sun spectrum peaks in the Roygbiv visible. Right, and in fact, it's the peak color of the sun is kind of a yellowy green, about 501 nanometers, 502 nanometers. All right, now the amount of energy at each wavelength for this 3,000 Kelvin star, that's the red one. Okay, now notice they're all nested. Okay, so the blue one is over all the others. And then the 5,800 yellow one is inside the blue one, but above all the others. And now the 3,000 Kelvin is below the first two, and it never gets above the first two. And that's because every wavelength, it puts out less energy per second, all right, because it's not as hot, all right? And a 3,000 Kelvin star has got a nuclear reactor in the core, but it's a pretty small nuclear reactor. So it only gets the surface to a certain temperature and no higher than that, all right? But that's all right. Now this 3,000 Kelvin star, guess what? Its peak color is actually over here in the infrared, right? And so that's one of the reasons that small stars, which tend to be red, are tough to see sometimes. If they're small, they don't put out a lot of light, even if you're up close. And if they're small, they tend to be red, reddish colored stars, and so they're kind of tough to see. But we've gotten a lot of them. I mean, it's possible for us to find them, but I think they still find them occasionally near the Earth. Now, down here, nested in all the way down here, is a human being at 310 Kelvin. Okay, that's us guys. All right? And so we're in the infrared. So the reason, and notice that we're way down the scale. We're square meter for square meter, you're not putting out as much energy as that 15,000 Kelvin star. All right? But, and most of your energy, you're not putting hardly anything in the ultraviolet. Most of your energy is in the infrared. And that's how, like the Army soldiers, they have infrared stuff so they can see people at night. Because, depending on where you are, if you're at like in a desert or something like that, the ground will cool off very quickly, but humans are always 98.6 degrees Fahrenheit. So they're always, at this temperature. So you can spot humans at night from that. Now, here's something I want to bring up to you. This whole idea of temperature, it doesn't just apply to stars. It applies to anything that's hot. All right, now this is an LED, so it's not an incandescent source. And I just looked up, color temperature, light bulb on the internet, and this is like the second site that I looked at. somebody called Halco light bulbs. It's an LED light bulb, and if you look at it closely by that red arrow, this is what you see. They have a color temperature designed, and you know what it is? It's the glass covering. They coat the glass with a certain coating of, like these fluorescent bulbs up here that we have in this room. They're fluorescent because of the coating on the inside of the glass. And the same thing with this. So they try to mimic a 2700 Kelvin star, square meter for square meter. Now it's an LED, so it's not perfect, but that's what they're trying to do. All right, so you can see that. And if you're an interior decorator or any kind of a designer or architect, this is a factor. Like in this room. Most of the lights in here are pretty low temperature because they're yellowy orange. You can see it, right? But I'm sure you've been in rooms where the fluorescents are really blue, and even film in the old days when we didn't do digital cameras as much as we do now, you could buy film from Kodak and Fuji that had a certain, that was set to certain temperature to be taken indoors with lighting of a certain temperature. And so that's what this is talking about. All right, so now let's go through this concept. I've talked about the diagram. Let's talk about the concepts behind it. So every object emits thermal radiation, whether you can see it or not. You emit a lot of infrared. Light bulbs, they're designed to emit Roygbiv, because that's what we need. Our eyeballs are Roygbiv. All right? And, but a stove can emit a lot of red, depending on the temperature, or it can emit a lot of zip-zap. I mean, visible. It might not, it'll be emitting some infrared, but if it still looks grayish black, the way the stove element does when it's off, but it's emitting heat, what that tells you is it's probably emitting infrared, but not it's not emitting much Roygbiv. But as it gets hotter and hotter, it'll turn red. All right, so stars are very much like that. Now, the peak wavelength, this is the key that is going to help us for understanding stars. The peak wavelength depends very, very simply on the temperature. Now, we're going to do some calculations here, so have your clicker and your calculator set. This is the formula. All right, this is called the Wiens Displacement Law. The peak or lambda max wavelength times the Kelvin temperature of the object, all right, is always going to equal. I mean, if it's not interfered with, or it's not behind some kind of a filter or anything, it's going to be 0.002898 meter kelvins. All right, and we call it there it is up at the top, the Wiens law or Wiens displacement law. And the displacement is seen in this, that as the temperature changes, the peak displaces on this diagram to the right. So this is high temperature. Now down here is lower temperature, and the peak is underneath and it's down. And it's to the right. All right. Now here's a 3000 Kelvin star. It's down because it's cooler, and it's to the right. And here's a 310 Kelvin human. All right. It's down and it's to the right. So the displacement means that the peak is displacing to the right according to this formula. All right. Now, go ahead and write that formula down. It's not hard to work with. All right. Make sure you have it written down because you're going to do a calculation with it on your iClicker question coming up. All right. So let's calculate, and I'm going to have it on the slide here. So, all right, yellow light. according to NASA, is about 5,700 nanometers. All right, so that's 570 times 10 to the minus 9 meters. All right, so calculate the temperature. All right, now you might want to do this on pencil and paper. If you know how to handle scientific notation in your calculator, you're going to be good. It's one of these 5 temperatures. Now, talk to your neighbor, kibitz with your neighbor, supervise your neighbor, get advice from your neighbor. Because it's a little, you're going to get good at this, but the first couple times might be a little, tricky. And you know what, guys? These are between 4,700 and 5,700. So I haven't made anything obviously correct or obviously wrong. You have to calculate. But let the numbers do the talking. And I'll work this out with you if you get it wrong. So just give it your best shot. Yeah, 570 nanometers. How many we got? 82. And if you want to use the 0.002898, that's actually 2.898 times 10 to the minus 3, if you want to use scientific notation. 2.898 times 10 to the minus 3. Okay, 110. 1 minute. And we'll go through this, so that you can. Twenty seconds. Yeah. You're not getting any of these? You're not. Are you using a calculator? So that means you're not using the calculator correct. So try doing it with pencil and paper. This is what I mean, for the next several weeks, we're going to be needing expertise with scientific notation. I mean, there's no other way to get around it. Question? Tote?
Yeah, and I put new batteries in it too.
Let me see.
It's not the old batteries from the.
These are alkaline energizers. I don't know what to tell you. Except, man, this is completely not working for Jack. Your calculator or your clicker is. Did you get anything in today? You're gonna have to. Hate to say it, but you're gonna have to get another one that works. So do you have a friend that you can borrow one from?
Right now,
No, well, for Thursday and for the exam.
it's fine. I'll figure it out. This is the one I borrowed.
Oh, you already, that is borrowed.
So I'll just try and switch out the battery and see.
Was it working before?
Yeah, it's just that I hadn't missed class because I was visiting universities. I was visiting PhD programs, so I haven't been able to use the clicker in weeks because I haven't been here. So yeah. So it's okay. I'll figure it out.
Well, wait a minute now. When did you put those batteries in?
In the beginning of when you told us to switch them out because the other ones.
Oh, so it actually might just put new batteries in, maybe.
Yeah, I'm gonna try it out.
Okay. Yeah. All right. All right. You got your answer in? Hurry up. 30 seconds. Mm-hmm.
Is the N in there just like a unit attached to the .020?
Yes, meters.
Oh, I thought that was
Yeah, meters times kelvins. Yeah. So when you divide by the lambda, you're dividing by some number of meters. You know, maybe nanometers or 570 nanometers. That cancels the meters in the numerator, and you're left with Kelvin for a temperature.
Gotcha. So that meters on the right is just a unit attached to that number. Okay.
All right, let's give this. All right, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. You guys did pretty good. Go ahead and show the students this. Yeah, C is the correct answer. Most of you got it. Go ahead and switch back, please. Here, so go ahead and make a note of that. Let's go through the calculation. All right, now, here's the calculation that you want to do. You want to divide both sides by lambda max, and that gets T by itself. Now, if you're trying to figure out the temperature, this is how you do it. All right? If you know the temperature is 500, so you go 570 times 10 to the minus 9. Now, that's not true scientific notation, but it's good enough for government work because we're in the middle of a calculation. All right? Now, on a calculator, it's easy as walking through the proverbial park. All you got to do is this thing in the black rectangle. Type in 0.002898 and then the divide by sign, and then on my calculator 570 and then the EE button and then the minus and then the 9 button and then hit equals and you'll get the answer. All right? So but everybody's, there's different scientific notation methods depending on the calculator. All right, so like the Apple, I can't remember what it is on Apple. On your iPhone, the thing is you can't use your iPhone or anything on the exam, so you're better off. Apple uses the EE button. But, like Texas Instruments, it might be something different. So depending on what you got. Anyway, so here's your calculation. And so what I normally do is I take that 10 to the minus 9 and I bring it upstairs. All right? and then I go 0.002898 divide. Oh, and by the way, notice, somebody was asking me, Dr. B, what is that M? Does that stand for mass? No, it stands for meters. All right, the wavelength down here is a number of meters. And the constant, that's a constant of nature, 0.002898 meter Kelvin. That's the Wiens displacement constant. All right? And notice in the second equation block here, the meters cancel out. And you're left with Kelvin, which is good because you want a temperature. All right? So if you're doing it in pencil and paper, this is what you've got to do. All right? And so if you take 0.002898 and divide by 570, that's what you get, 0.0000050842 times 10 to the 9. Nasty. Really nasty. So what you do is, instead of dealing with 10 to the 9 Kelvin and a really small decimal, just move the decimal point over. Now watch, here it comes. It's animated. It's kind of cute. All right, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there you got it. 5084.2 Kelvin. All right? Daniel.
Couldn't you also do 0.002898 times 10 to the 9 over 570?
You can. Mm-hmm.
Okay.
Yeah. All right. I'll see you guys on Thursday. We'll do some more of this then. You're dismissed. I was hoping to do one more question, but I'll get my cursor back.